All right, so in this video, we're going to look at balancing chemical equations. Now, this set of notes is pretty much just the basics of how to balance different reactions. So we'll look at some more advanced reactions later on, but this is a great place to start. So I'm going to get my pen set up here. That's a terrible color. There we go. All right. So first question, right? What is a chemical equation? Well, primarily speaking, okay, we're just looking at something that describes a chemical change. And a chemical reaction obviously is going to have different parts, okay? So if we look at this reaction right here, we have a metal by itself, all right? We've got an acid. This is hydrosulfuric acid right here, hydrosulfuric acid. And we're making a new salt, right? I know it's a salt because it's a metal and a non-metal, right? So there's my new salt. And I've got hydrogen, which I know, hey, anytime hydrogen's by itself at room temperature, it's going to be a gas. So this is describing definitely a change. On the left side, we have the reactants. On the right side, we have the products. The arrow in the middle is called the yield arrow. All right. Now, when we look at those reactants, that's the chemical that we're starting with. Okay, that's the thing that exists before the reaction occurs. It's always, it is typically written on the left side of the equation, okay? The product is the new chemical formed by the reaction. It's usually written on the right side of the equation. Now, I say usually and typically because technically the arrow points at the products, all right? It's not always left and right. What do I mean by that? Well, H2 plus O2 yields water. All right, so here, these are the reactants, and I have one product. This is a synthesis reaction. We'll learn more about the types later on, but this is a synthesis reaction because I have two reactants making one product. We're making one thing from two parts. Now, this same reaction can be done in reverse. It's called a decomposition reaction, but I'm going to write it the same way. Now, in this case, all right, we have completely different things. This is the product, and this is the reactant. The thing that matters here is where is the arrow pointing, all right? If it's pointing to the left, all right, the arrow always points at the products, all right? Arrow always points at the products. Typically, because we read left to right, this is how we want to write things, okay? Now, reactions also involve, chemical equations also involve subscripts, which are going to show you how many atoms of an element are present in a molecule. So if you look at H2O, we've got 2 atoms of hydrogen. We've got 1 atom of oxygen. There are coefficients, which are going to show you how many molecules there are of each specific particular chemical. We call those species. So here I have 3 waters, so this would be 3 water molecules. Now, when you have a reaction take place, all right, so in this case, 2 hydrogen molecules react with 1 oxygen molecule to make 2 water molecules, what you are describing is the transformation of, in this case, 2 reactants into 1 product, right? Or it could be any number of other things, but you're describing that transformation. Now, we need this coefficient here, and we need this coefficient here. Otherwise, the animation won't work right. And the reason I say that is every time you have a reaction, it has to follow the law of conservation of mass, which says that in a chemical reaction, in a normal chemical reaction, in a non-nuclear chemical reaction, matter is neither created nor destroyed, okay? So that means the number and types of atoms going into the reaction has to be the same as the number and type of atoms coming out of the reaction. That means it's balanced, all right? So when we say balance an equation, what we're saying is, hey, make sure the law of conservation is conserved. So if we look back at the reaction we just had on the screen, where's my eraser? Just a second. Anyway, if we look back at the reaction we just had on the screen and we just write it like this, hydrogen and oxygen make water. Well, no, not really, because what I actually have is I have two hydrogen atoms, I have two oxygen atoms, and that means I haven't used that guy, right? I've used this hydrogen, it's right there, two hydrogens. I've used that oxygen, it's right there. Well, where is this dude? All right, we got to account for him. So in order to make another water molecule, right, I've just got this oxygen floating around. I need two hydrogen molecule, or sorry, a second hydrogen molecule in order to go out. So there's that one, and there's that one. So let's look at that. Here's an unbalanced equation. Same thing, just with prettier pictures than I just drew. On the reactant side, I have one carbon atom. There it is, right there. All right. I have four hydrogen atoms, all four, H4, and I have two oxygen atoms. There they are. On the product side, I still have one carbon atom, but now I only have two oxygen atoms plus one. So 2 plus 1 equals 3 oxygens, right? And this plus sign really means if there's oxygens on two different molecules, add them up. So these two go together, all right? And then I have two hydrogens, all right? We can see that there. Now this is unbalanced, all right? I can see based on the colors, right? On this side, I have too many oxygens, and I have too few hydrogens, right? I only have 1, 2. Over here, I have 1, 2, 3, 4. Over here, I have 1, 2. I got 1, 2, 3. So I haven't used the things that I've circled. That's the problem. So when we balance it, we add those coefficients in. So I need two oxygens on the left, all right, two oxygen molecules, and I need to make two water molecules on the right to make sure everything is used up. So are there some rules for this? Like, how do I know to put those twos there? It's not just a guessing game. All right, first, we know that matter can't be created or destroyed. We know that the subscripts cannot be added, removed, or changed. This is really important. Do not change the subscripts in order to balance something. So where is the subscript? These. These are immutable. Do not change them. If you change the subscripts, you change the chemical. Now it's not, CH4, this is methane. All right. There is no such thing as CH5. All right. There is a CH2, but methane looks like this. CH2, actually, no, sorry. There is no CH2. You can't make any of those other things. So do not change the subscripts, all right? You can only change the coefficients. That's totally allowed. And when you put coefficients out on the equation itself, they go in front of the chemical formulas, never in the middle, all right? A couple extra things. Now, this is my rules to help you. First, try to balance your big formulas first. So if you have like silver nitrate, like AgNO3, that's a big formula. It's got a lot of different elements in it. Try to balance it first. If you have free elements like O2 or H2 or a metal all by itself like Ag in that first equation, leave it till the end. It'll be easy to fix. If you have polyatomic ions on both sides of the equation, you can balance them by what we call grouping, and we'll look at that in closer detail. Always leave oxygen and hydrogen to the end if at all possible. They usually balance themselves out. And there is not a particular way to balance equations. You don't have to follow a specific pattern every single time. It's okay to be creative, all right? And we'll look at some creative ways to solve equations as we move forward. When you group polyatomics, that's probably the fastest way to balance some of the bigger equations. So I'm going to encourage you to practice that anytime we can. But let's look at some simple equations because this is the simple introductory lecture. So I like the way that this PowerPoint, or I like teaching off this PowerPoint because it's pretty organized. So I'm going to show you what it looks like on here because, I have to make these little lines and grids and stuff. And then I'm going to show you how to do it on a piece of paper. Okay, so first let's look at this. we have nitrogen as a reactant. We also know it's a product, right? It's on both sides. We have hydrogen as a reactant. We know it's on both sides. We need to start by counting how many we initially have. So on the left, on the reactant side, right, and remember, this is the reactant side. Here is the product side. So on the reactant side, we have 2 nitrogens. We have 2 hydrogens. On the product side, we have 1 nitrogen. We have 3 hydrogens, okay? So I can't fix this with a whole number, right? I can't multiply 2 by a whole number and get 3. So can't do that one. But I can definitely multiply 1 by a whole number to get 2. So I'm going to put a 2 in front of this product side ammonia molecule. Now, what that's going to do is it's going to change that number to 2, because 2 times 1 is 2, right? There's an unspoken coefficient there. And 2 times 3 gives me 6, right? Anytime I change a coefficient, I need to update my running count, right? Now, 2 and 2, they're equal, so nitrogen is good. I look at the hydrogens. I have 2 and 6. There is definitely a whole number. I can multiply 2 by to get 6. Hopefully you know that's 3. So I put a 3 there. 3 times 2 H's is 6 H's. So I have 2, 2, 6, 6. All right. I'm going to go back to the beginning. So that is balanced. So that is balanced, right? I don't need to put anything here. If I really want to, I can write a 1. All right. This looks great on PowerPoint screen. Let's go back to our initial look and see what it would look like if we were doing this on a piece of paper. So I'm doing like a worksheet or a practice problem, or I'm on scratch paper where I'm taking a test. I write out my equation. I recommend you throw little blanks out in front just to remind you, hey, I need to make sure that everything has a number, even if it's just a 1. Draw a line between the yield arrow. Make a list. NH. Make the same list on both sides. All right. We're going to do a count. So I have 2 nitrogens on the left. I have 2 hydrogens on the left. I have 1 and I have 3. Now, same thing as before. I can't change a 2 into a 3, but I can change a 1 into a 2. So I throw that 2 coefficient there. Remember, there's a 1 here. So 2 times 1 is 2. Now, this is the key. Mark out things as you go. Don't erase them. That way, if you, well, 1, if I'm grading it and you get it wrong, I can look and see if you made a math mistake and maybe give you some partial credit. But 2, if you have to go back, you don't have to like recount over and over again. You just erase 1 number and the little slash and you're good to go. 2 times 3 gives you 6. Now over here, 3 times 2 gives me 6. 2, 2, 6, 6. We're good. Throw 1. And we're done. This is what I usually teach on paper. Whoa. Right? That's what it should look like. That's how I balance. If I can't do grouping, if it's complicated, just write it out. Make a list. Make the list in the same order on both sides and count your atoms. All right, let's do another. Okay, there we go. All right, I have it would be potassium chlorate, and I have potassium chloride and oxygen gas being made in our reaction. So let's do it my way. All right, we're going to go line down the middle, right? Separate the products from the reactants. Make the same list on both sides. Count them up. KClO. We have 2, 1, and 1. All right. 1s are good. I have O's 2 and 3. What do I do? All right. Well, in this case, I'm just going to take whatever subscript, right? Because I have 2 and 3. I know the least common multiple of these two is going to be 6. So I'm just going to put a 2 out front there. I'm going to put a, well, let's just see what happens. I'm going to put a 2 right there. So we're going to go 2, 2, 6. All right. Put a 2 right there. 2 KCl, 2 KCl. And put a 3 there and get 6. 2, 2, 6, 2, 2, 6. Everybody's good. We're balanced. So in this case, right, I'm going to put a dotted line around that 2. I just switched these 2 coefficients to get a least common multiple. Now, let's see what happens if we do it the organized way. All right. We have K, Cl, and O. 1, 1, and 3. 1, 1, and 2. 2s and 3s there. Just like that. There we go. And there we go. Happy times. All right, here's one that's a little bit more complicated, okay? So I'm going to look at this and I'm going to say, well, I have oxygen in 2 different places, right? So sometimes these can be a little tricky. Combustion reactions can have big numbers, right? But we just approach it the same way. Make a list. 2, 6, 2, C, H, and O. 1 carbon. I have 2 hydrogens. And remember, I have to add because I have oxygen in 2 different places. So 2 oxygens on carbon dioxide and 1 on water give me 3. All right. So we'll do carbon first, right? Do my nonmetals first. So that's a 2. All right. That gives me 4 plus 1. That gives me 5 oxygens. 2 to a 6. Yeah, I can probably do that. That'll work. 3 right there. So that's going to give me 6. Now's when we have a little bit of math, right? 2 times 2 plus 3 times 1 gives me 4 plus 3 equals 7. All right. So what now? Carbon's good. Hydrogen's good. But I need to turn a 2 into a 7. And we know you got to have whole numbers in these blanks. But let's be creative. What if I didn't have to use whole numbers? 2 times what gives me 7? That's pretty easy math. 3.5. 7. So I have 2, 6, 7, 2, 6, 7. So that would mean this is a 1. All right. Can I stop here? No, absolutely not. I'm being creative, but I can't stop. So I need to turn that decimal right there into a whole number. It's got a 0.5. So I know that anything, right? I know that if I have 0.5, right, and I multiply it by 2, I'll get a whole number. I'll get number 1. So I'm just going to multiply every coefficient by 2. And that's going to give me 2, 7, 4, and 6. Let's see if that's right. Look at that, 2, 7, 4, and 6. Okay, so this is a creative step where we can look at that decimal right there and we go, okay, that does solve it. I can't leave a decimal though. Never leave the decimal. Just double all the coefficients. If I got like 3.33 there, well, triple everything. 3.25, well, quadruple everything, right? 3.2, multiply everything by 5. So we can be creative, right? Use decimals, but then just multiply them out, right? Let's look at another one. Have iron and oxygen gas. Molecular oxygen is making iron 3 oxide, all right? Well, same thing. Draw a line. FeO. I have 2. I have 1. 2. Notice 3. Put a 2 there. That does that. Up 2 and 3. So it's flip them. 3, 2. That's going to give me 6 oxygens. That's going to give me 4, 6. So I know this is wrong now. Scribble it out. Put a 4 there. 4, 6. So that's good. That's good. 4, 3, and 2. There we go. All right. So that's the basics behind. That are the basics behind balancing chemical equations. Excuse me. If you have any questions, let me know, and I'll be glad to give you a hand. But in the next video, we'll look at a couple more complicated ones. All right.